Hi grade 11s and grade 12s. If you are catching up on this video, I'm back again with another exciting and interesting video where we'll be exploring theorems and their categories. So just a quick recap. So on the first lesson of this series of Euclidean geometry tutorials or lessons, we've covered the introduction of Euclidean geometry by revising all the theorems that we've learned in the previous years, your grade 10, your grade 9. And then on the second video or the second lesson, we look at theorems that are examinables. That are examinable, which means the theorems that you need to know how to solve their, when I say theorems that are examinable, I'm referring to those theorems where you'll be asked to derive them using first principle, okay? So if you are joining in for the first time, I'll advise you to watch those two videos or lessons so that you can understand what I'm referring to. So in these lessons, we'll be going through a very important section called Exploring Theorems and Their Categories. As I also mentioned in the first video, I mentioned that these theorems are categorized into three areas. The first one is I call them the families, or you can call them categories. It's the family of angles and centers. So all the theorems that falls under angles and centers are these ones. Then we've got the second ones. We've got the family of cyclic quads. It's these two. And we've got family of tangents, which is these three. Okay. So in this lesson, we'll focus on angles with centers. Okay. So theorems involving the center of a circle. Okay. So the first theorem that falls under this category, it says the line drawn from the center of the circle perpendicular to the chord bisects the chord. And in short, you can say it's a line from center perpendicular to chord. Again, grade 11s and grade 12s. The reason why I put a star here is to remind you that this is one of the theorems that is examinable. And I believe by now you know what I mean when I say examinable. So you need to know how to prove this using first principle. Okay. Now, let's explore what this theorem is saying. So this theorem is saying if a line is drawn from the center of the circle. So here is a line drawn from the center of a circle, so that it is perpendicular to a chord. So if it's perpendicular to the chord, as you can see, perpendicular to this chord AB, then it will bisect, it will cut in half the chord. So it means this will be equal to that, as they show in this picture. So we had this before, and then this line divided the chord in half. That is all you need to know, or that is the key thing that you need to know about this theorem. And it says if OM is perpendicular to AB, then AM is equal to MB. So what they are saying here, it's what is being shown in these two diagrams. I hope this makes sense. And you can summarize this by saying perpendicular line from center to chord, which is the same as line from center perpendicular to the chord. Okay? As you can see here, it says the proof of this theorem is on the next slide. But I'm not gonna go through this. So if you don't know how to solve this, make sure that you catch up on my lesson 2 of this Euclidean geometry series, where I explain in details to say what do you do, how do you go about this. Okay, so we'll move to the second one. So we are still under centers with circle. Now we've got what you call theorem converse. So this is the reverse. So I take converse as like a reverse. For example, we know that if x plus y is equals to 10, then this is the same as 10 is equals to x plus y. It doesn't matter where you read it from. So if you go this way and you go this way, it's still the same thing. So this is more or less the converse of theorem 1. So now it says the line segment joining the center of a circle to the midpoint of a chord is perpendicular to the chord. And then the summary there, it says line from center to midpoint to a chord. So you'll see here there's no star. Why? Because this converse, it's not examinable. It's not examinable. What do I mean by this? I mean, they will not ask you to prove examinable. They will not ask you to show the proof. They will not ask you to show the proof steps like here. No, they won't. What you need to know, you need to be able to apply the theorem. Okay? So what does it mean? The line segment. So it's telling you the line segment joining the center of a circle. So this is a line segment. Okay? To the midpoint. So if it's a midpoint, if it's cutting this if it's cutting AB in half, then it only means one thing. This line is perpendicular. You can't have a circle. Sorry, my drawing is bad. You can't have this center and a chord. You can't have a line that cuts here. You see, this line is not perpendicular to this line. So there's no way that this line can be equal to this. In a nutshell, that's what this theorem is saying. This theorem is saying if we've got a circle and a chord, and we've got a line that is cutting this into two, then it only means that this is 90 degrees. I hope that makes sense. Nothing too difficult there. Okay, now we go to theorem number 2, which says, and again, I repeat what I said in the first lesson. It doesn't matter. Okay, how do I put this? You see on my theorems here, this one says it's theorem 2. In other books, this theorem 2 might be theorem 3. And this theorem number 1 converse might be theorem 2. It doesn't matter whether it's called theorem 1 or theorem 2 or theorem 10 or theorem 10 or 15. What is important is for you to know which theorems we are referring to. They will never ask you in a question and say, give us a define theorem number 7, because we don't know which one is theorem number 7. So what they will actually do, and I've seen in other questions, they will say the line drawn from the center of a circle perpendicular to the chord, and then they leave a space and say complete the theorem, and all you have to do is say pass it, bisect the chord. But they will never say define theorem number 1. No, it doesn't work like that. Okay? So this one says the perpendicular bisector of a chord passes through the center of a circle. It's more or less the same thing as what I've explained here. So the perpendicular bisector. So a line that cuts the chord into two equal parts, it will always pass through the center. We don't care whether it will end at the center, it will end in the middle, or it will go to the other side of the circle. We don't care. What we know that is that the line that perpendicular cuts the chord into two equal parts, it will always pass through the center of the circle. And that is what this theorem is saying. And in short, you can summarize that by saying perp bisector of a chord. Okay. Now we move to theorem number 3. We can see there with a star. I believe you know what the star means. It means this theorem is examinable. So you need to know how to solve this using first principle. Okay. Again, one of my favorite theorems. It says the angle subtended by an arc at the center of the circle is double or twice the size of an angle subtended by the very same arc at the circumference. Again, grade 11, grade 12. If you don't know what is an arc, if you don't know what subtends means, if you don't know what is a circumference, please make sure that you watch video number 1, where I dissected. I did not bisect, but I dissected a circle. I cut the circle into different parts to show you what is an arc, what is a chord, what is a radius, and so forth and so forth. Okay, so the summary of this, it says angle at center is twice the angle at the circumference. So what this theorem is saying is that if you've got A, B, and C here, this angle that is subtended by an arc at the center is 2x, the angle subtended by the same arc, but not at the center, but at the circumference. So 2x is equal to that. It's another form of representation. So we've got diagram 1, diagram 2, diagram 3. These things are saying the same thing. So all you have to do, check where the arc is subtending the angle at center and where the same arc is subtending the angle at the circumference. again, it's the same thing here. Arc subtends an angle that is twice the angle at the center, and here the same arc subtends an angle at the circumference. Okay, this one says proof on next slide. Again, we are not going to go through this. If you want to know how to solve this is what I mean by first principle. By first principle, you have to show what is the first principle. So when I refer to first principle, I'm talking about this. You're giving your required construction and your proof. Again, refer to the second video that I've uploaded. Okay, I think this is the last one. Yes, the last one, it says theorems involving the center. We are still on the same one. It's theorem number 4. It says the angle subtended at the circle by a diameter is a right angle. So again, this again is this. It's similar to the previous theorem where it says this is 2x, and therefore this will be x. Why? Because this arc subtends an angle of 180 degrees at the center. The very same arc subtends an angle of 90 degrees at the circumference. So this will be 180. So this will be 180 degrees, and this will always be 90 degrees. Always. So the diameter subtends a 90-degree angle at the circumference. That is what this theorem is saying. And we can also summarize it and say angle in a semicircle. Okay? So it says here, given AB, the diameter of a circle passing through center L. So this is what I've already explained. Lastly, the converse. If the angle subtended by a chord on the circle is 90, then the chord is a diameter. It's reverse. Converse is reverse. We are going backwards. So now, if this is 90 degrees, there's no other way. This must be a diameter. That is a reverse. That is what this theorem is saying. And we summarize this by saying chord subtends 90-degree angle. I hope these theorems of centers, these theorems that involve centers of a circle are clear, are loud, and you will not struggle to explore these theorems in equations. Thank you. Okay, so we'll now explore another form of set of theorems, or another family. As I mentioned, I call them the family or the category, and this one, it involves cyclic quadrilaterals. Okay, again, if you don't know what is a cyclic quad, that has been explained in the first 2 videos. Okay, so again, I will share the definition. It says a quadrilateral is any 4-sided figure. Okay, so we don't care as long as it's a 4-sided figure. If you can recall, a triangle is a 3-sided figure, but a quadrilateral is any 4-sided figure or polygon. But a cyclic quadrilateral is a 4-sided figure with all its vertices like the circumference of a circle. So if you've got this, it's a quadrilateral because it's a 4-sided figure. Okay, but the moment these vertices they lie on the circumference of a circle, this is no longer a quadrilateral, but it's called a cyclic. Okay, so let's see with the diagrams that we have there, 1, 2, 3, and 4. It says cyclic quad A, B, C, D. Whether you call it A, B, C, D, or you say D, C, B, A, or C, B, A, D, doesn't matter which direction we are taking. As long as all these 4 vertices are touching the circumference, it's a cyclic quad. Okay, again, cyclic quad, they say cyclic quad PQRS. So PQRS. But they say PRS is not a cyclic quad. Why? Because let's look at the pattern. For you to move from P to R, you're going to move like this. P, R, S, Q. So this is not a closed figure. It's not a 4-sided figure. Okay, that's why it's not a cyclic quad. But if you come here and say W Q P R, now the question is this a cyclic quad? And I hope you are shouting and say no. Why? Because Q is not a point on the circumference, it's a point outside the circumference, so it doesn't touch. Although this is a four-sided figure, yes, it's a quadrilateral, but it's not a cyclic quadrilateral. Again, why is this PSTQ is not a cyclic quad? Because T doesn't touch the circumference, so T must be somewhere there. So this is a quadrilateral, but it's not a cyclic quadrilateral. I hope you are able to understand what we mean by quadrilateral and what we mean by cyclic quadrilateral. Sorry about that. Okay, let's go back to the theorems. It says, this theorem number 5, it says angles subtended by a chord or an arc of the circle on the same side of a chord are equal. So angles subtended by a chord on the same side of a chord or arc are equal. Okay, there is no star here. Why? Even though there's a proof here using first principle, they will never ask you to derive this. They will never ask you to prove this in an examination. So that's why there's no. So this is just extra information that you need to know for your information. So let's see what they are saying. They say angle subtended by a chord. So this is a chord. It subtend an angle here, A. The same chord, it subtend an angle there, B. So these angles will be equal. Again, this arc subtended an angle there. The same arc subtend an angle there. Oh, this is a mess. Let me see if I can find an eraser so that you can see what's happening here. So this arc, the same arc subtend an angle there. So whether you use chord or an arc is the same thing. So this angle A will always be equal to angle B. At the same time, that's why the resonance says angle in the same segment. So these two angles are in the same segment. Again, I explained in the first lesson why I dissected and explored a circle to say what is a segment, what is a minor segment, what is a major segment. So these two angles are in the same segment, that's why they are equal. Okay, I'm not going to go through the proof. The converse, the reverse of this theorem, it says if a line segment joining 2 points subtends equal angles at 2 other points on the same. Okay, so if we've got a figure like this one, it's not a quadrilateral. Okay, if we've got a figure like this, but you discover that this angle is equal to this angle, then it means there's an imaginary circle that is passing here. That's why we say this thing is a cyclic quadrilateral. So if this angle is equal to this angle, and again this angle is equal to this angle, even though they are not passing through a circle, just know that there's an imaginary circle that is passing there. Hence, this thing become a concyclic quadrilateral. Very, very important. This you'll find in a question. The circle will be hiding somewhere in between a rider. Okay, so let's read that again. If a line segment joining 2 points, so a line segment joining 2 points, they're joining points there, point A and point B, subtends angles that are equal. So this is angle number 1, subtend angle number 2, and these angles are equal on the same side of the segment, then these 4 points are concyclic, lie on the circumference of what? Of an imaginary circle that is there. Okay, let's look at the theorem 5 corollaries. So we are exploring more corollaries, and we've got 3 different. So BC is a chord, so this chord and EF is a chord. Equal chords subtend equal angles at the circumference. So this will, if these two chords are equal, then the angles they are equal. So equal chords, equal angles. That's number one. Equal chords subtend equal angles at the center. Again, chord BC and FE are equal. Therefore, they subtend, they extend, they make an angle that is equal at the center. And if these two chords are equal, it means the angles will also be equal. Equal chords, equal angles. That's the summary. Number 3, equal chords of equal circles subtend equal at the circumference. Very important. Let's read that slowly. Equal chords of equal circles subtend equal at the circumference. So here we've got two circles, okay? And if you check this, okay, we've got circle there, we've got the circle there, and they say angle A is equals to angle D, and angle G is equals to angle H, or there. Why? Because these equal chords of equal circles. So if two circles are equal, okay, I think that I understand what they're saying here. So if two circles are equal, and they have a chord that is equal, then that same chord will subtend equal angles at the circumference. I think what is missing here is equal angles. So equal chords of equal circles subtend equal angles at the circumference. Sorry about that. The summary, they say equal circles, equal chords, equal angles. But this is a very rare case. In most cases, this is the true, especially this one. So this is the first priority. This is the second priority. This is the third priority. So this one you need to know by heart. Even this one is a rare case. You will hardly get a question where you put two equal circles. But if that comes, you need to remember this theorem. Theorem number 5, corollary. Equal circles, equal chords, equal angles. Okay. Theorem number 6. There's a star there, which means this is examinable. The opposite angles of a cyclic quadrilateral are supplementary. Again, we've got 4 points on the circle. These angles that are opposite are supplementary, which means they are not equal, but they add up to 180 degrees. Similarly, these ones, they add up to 180 degrees. That's what this theorem is saying. If A, B, C, D is cyclic, then A plus C is equals to 180, and B plus D is equals to 180 degrees. Explained and dealt with in the previous tutorials. Theorem number 6. Converse. If the opposite angles of a quadrilateral are supplementary, then the quadrilateral is cyclic, is a reverse. The first one, it says opposite angles of cyclic quads are equal. Now they're saying if the two opposite angles are supplementary, which means they add up to 180 degrees. Therefore, it means that the quadrilateral is cyclic. If the opposite angles of a quadrilateral A, B, C, D are supplementary, then A, B, C, D is a cyclic quadrilateral. Straightforward. It's a reverse. Again, I'm moving fast grade 11 and grade 12 because this is just the theory that you need to know. You need to read through this and understand what is important, and you will see when I do questions. That's where I'm going to spend more time explaining how to solve these problems. Oh, this one is my favorite. I love this one. It says the exterior angle of a quadrilateral is equal to the interior opposite angle of the quad. Then the quad is cyclic quad. Okay, this part is really not necessary. The exterior angle of a quadrilateral is equal to the interior opposite angle. That's where you need to end. This part it's just extra information that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angles. Again, an exterior angle, if you don't know what is an exterior angle, that has been dealt with in the first lesson. So this angle, which is an exterior to the cyclic quadrilateral ABD, this will be equals to A Straightforward. Remember, when it comes to a triangle, there we are saying the exterior angle of a triangle, the sum of the opposite interior angles, A, B, C. C is equals to A plus a triangle. But when it comes to a cyclic quad, we are saying C1 is equals to A here. Two things that you need to take into consideration and that you need to bear in mind. Cyclic quad, the opposite angles, the exterior angle is equal to the interior opposite angles. The exterior angles of a triangle is equal to the sum of the opposite interior angles. Okay, this is the converse, the reverse. If an exterior angle of a quadrilateral is equal to the interior opposite angle, then the quadrilateral is a cyclic quadrilateral. Straightforward. If this is equal to this, then it means there's an imaginary circle that is passing there to make up this a cyclic quadrilateral. Simple stuff. Strategies to prove that a quadrilateral is cyclic. Again, this is a very important diagram, but I will show you how to use it when I start exploring and solving geometric riders, so that I can show you. This question says we must prove this. Okay, if they ask us to prove this and we've got this is how you go about it. If they ask us to prove this and we've got this is how you go about it. But this is a very nice diagram. I call this the cheat sheet. Very important. It summarizes everything. So it shows you all the steps that you need to follow when you want to prove that a quad is cyclic. So you've got options there. So this will depend on what is given on the question, and you build up based on what is given to you, and you'll be able to solve that. Okay, that concludes this section of exploring quadrilaterals which are cyclic. Again, this is category number 2, or family of cyclic quadrilateral. We will now move over to theorems involving tangents. Okay, moving over to category of tangents, we'll start with theorem number 8, which says, so now we are dealing with tangents. Okay, a tangent, and I believe you know what is a tangent. A tangent is a line that touches the circumference of a circle at one point. Okay, again, that was also covered in the first lesson of this Euclidean Geometry series. Okay, so it says a tangent to a circle is perpendicular to the radius at the point of contact. So if you check here, ACB is a tangent. So there is a tangent, it touches a circle at one point outside the circumference, and it says then a line that is drawn from the center of the circle to that tangent is perpendicular to the radius. Okay, similarly, maybe before I go there, maybe let's read that again. A tangent to a circle is perpendicular to the radius at the point of contact, and the reasoning there in summary, it says tan perpendicular to radius, or radius perpendicular to tangent. If you recall, when we're dealing with centers, when we had a chord, which is a straight line like that, they said a chord is perpendicular to the radius. It's more or less the same thing. Here it's just that the chord is outside, and it's no longer being called a chord, it's called a tangent because it touches a circle at one point outside the circle. But again, it's perpendicular to the radius. Okay, it says the e.g. if OC is a radius and a tangent AB touches the circle at C, then AB is perpendicular to OC. That's what I was explaining. Again, this line might also be a diameter. So as long as it passes through the center of the circle, it will perpendicular cut the tangent at 90 degrees, or perpendicular, or at right angle. Now, the converse, and I've realized that as I was explaining the theorem before, I also touched base on this one. It says, if a line is drawn perpendicular to the radius, so now it's a reverse. The line is now perpendicular. Okay, if the line is drawn perpendicular to a radius, at the point where the radius meets the circle, then the line is tangent to the circle. straightforward, learners. Straightforward. It's a reverse. If you know the main theorem, then the reverse or the converse will be easy to analyze. And all these converses, the reason why I'm explaining this converse, you will see when we are solving geometric riders. If you don't know what is a geometric rider, it's a geometric rider. It's a problem where you need to solve how do I put this? It's a question that will be asked to you where you need to apply all these different types of theorems to solve the questions that will be asked. So what is very important is that every time you are solving those geometric riders, be able to apply this theorem and know their converses, because they will ask you, prove that this line is a tangent, and this way you'll apply this type of a converse theorem. Okay, so it says there, if line ABC is perpendicular to radius OB, okay, line ABC is perpendicular to line O, then ABC is a tangent. That's what this theorem is saying. So whether you go this way or you go this way, it's the same thing. Theorem number 9, it says two tangents drawn to a circle from the same point outside the circle is equal. Okay, two tangents, I'll just say are equal. I don't know, this is equal. Two tangents drawn from the center of the circle outside the circle are equal. So if you look at this, we've got a circle, and we've got tangent number 1, got tangent 1, and tangent number 2. We call these lines tangent because they are drawn from outside the circle and they touch the circle at 1 point each, at A and B respectively. And if they are drawn from the same point, then they are equal. That's what this theorem is saying. If two tangents are drawn from the same point, then they are equal. Straightforward. Because if you look at this is a 90 angle. Why are we saying this is a right angle triangle? Because we've proven, or we've seen in the previous theorem, that tangent is perpendicular to radius. So there's your tangent, there's your tangent, and there's your radius, and this is 90 degrees. Okay, if this is 90 degrees, then therefore this is a right angle triangle. Theorem number 10, which is the last theorem, it says the angle between a tangent and a chord is equal to the angle in the alternating segment. Again, very important. What is an alternate segment? What is an segment in the first place? Again, I repeat. I explained this in the first lesson. So it's very important to go through the first lesson first, so that you know and you've got the foundation of these terminologies, because you will, in this topic, you've got tons and tons of terminologies that you need to familiarize yourself with. So when they say alternating segment, you need to know that we've got two types of segments. We've got minor segment and major segment. And what makes up a segment? A chord is the one that divides a circle into minor and major segments. Okay, so this theorem says the angle between a tangent and a chord is equal to the angle in the alternating segment. So we've got a circle there, we've got a tangent there, then this angle that is between a chord and a tangent, it will subtend an angle in the alternating segment, which is what they did there. So this angle there will also be equal to this angle there, and this angle there will also be equal to that angle there. Okay, very, very important and straight to the point. Again, it says proof on next slide. We're not going to touch base on this. This has been explained in lesson number 2, where we were going through examinable theorems. Lastly, if we look at the converse of that theorem, which is the reverse, it says if a line is drawn through the endpoint of a chord, making with the chord an angle, making with the chord an angle to an angle in the alternate segment, then the line is a tangent to the circle. This is a bit confusing, but what is this is saying is that if we've got this angle that is between a tangent and a chord, and this angle is equals to the angle in the alternating segment. Therefore, this is a Tancourt theorem. It's a reverse of Tancourt theorem. That's why they say converse Tancourt theorem. So if this is equal, then we know that there's a circle that is passing here. There's an imaginary circle that is passing here. Hence, this diagram here. So, what is very important about these theorems? Converse are the reverse of the main theorem. And converse will be tested on questions where you'll be asked to prove that either a theorem is a Tancourt theorem, either a quadrilateral is a cyclic quad, either like you'll be asked different types of questions. And again, I repeat, most of these theorems, what I'm doing here, I'm just covering the theory. They will make sense while I start doing problems, which is what I'm going to cover in the next lesson. Because the main priority of me going through all these lessons is to make sure that you've got the right information, you've got the right foundation, and you know all the main basics, together with the terminologies, together with the necessary knowledge that you need to apply to be able to solve geometric riders. At the end of the day, they will never ask you to define a theorem. They will always ask you to apply that particular theorem. And that is what we'll be covering in the next lesson. I hope grade 11s and I hope grade 12s, if you're catching up on this, the videos that I've covered now, they gave you the foundation that you need, and I believe now we are confident enough to be able to solve geometric riders, and you'll be able to be competent and be ready to face those examinations. Geometry is all about theorems, theorems, theorems. Know your theorems, know how to apply them, know how to prove, and you'll see this will be a walk in the park. Until we meet again, have yourself a lovely day. Thank you.